the normal distribution is used in statistics where we're dealing with continuous quantities, and it is seen in many examples throughout nature. In this example, what I've pulled out is heights of a sample size of adult males, and there's about 1 million of them. Now, I've broken the classes. This is just a frequency table to show you how they're distributed. And I've broken each class into 16 centimeters, and as you can see, I've got the bulk of the modal class is this one here. Now, because it's a frequency table and it's a continuous distribution, we can represent this as a histogram. All my bars are of equal width, but it is the area that is proportional to their frequency. Technically, because the widths are the same, it is also their heights that are proportional to the frequency in this question, but normally it's just the area. Now, because I've got so much data in this question, I can break these categories down much smaller. So if we halve the size of each class width, so these are now, we've got class widths of 8 centimeters, and we look at that distribution, you can see we're starting now to get towards a shape that's got a big peak in the middle. We have a lot of people all in the middle around 180 centimeters, but as we go out towards the edges, we get far fewer people. And we can carry this pattern on. This is down at 4 centimeter class widths, 2 centimeter class widths, 1 centimeter class widths, and I think this one's 0.5 centimeter class widths. Now, as you can see, what we're tending towards is a curved shape. It's typically called a bell curve, and this is our normal distribution. It is found in all sorts of examples throughout nature, where we've got a lot of people all around a central value, but as you go out towards the extremes, you get far fewer, and you get sort of a similar symmetrical proportion on both sides. Now, in our normal distribution, we don't use it to represent frequencies, but to represent probabilities. So there's our normal curve. It's symmetrical about that central point and has this typical bell shape to it. Now, this is in your notes. Because it's a probability distribution, just like we saw in discrete random variables. Now, that's discrete, it's very different, but the thing they have in common is that their total probability is 1. So we use the area under the graph to represent the probability here. So the area under this curve will always be 1 for any normal distribution. The second important point is that these values here aren't hitting the axis. The x-axis is actually an asymptote to the curve, so it's never impossible to get a really, really low value. It's just incredibly unlikely and similar for a very high value. Because it's symmetrical about the middle we also note is the highest point on the curve. The highest point on the curve is going to represent my modal value. Because it's symmetrical, then the median is going to be in the same place, and also the mean. So we can say the mean is approximately equal to the median, which is approximately equal to the mode in a normal distribution. And similarly, to do with the symmetry, Q1 is going to be the same sort of distance from Q2 as Q3 is from Q2. So we can say Q2 minus Q1 is approximately equal to Q3 minus Q2. And you should recognise both of these as tests for skewness, and therefore you can conclude that there actually is no skewness in the normal distribution because, of course, it is symmetrical. Now, as we said, the area under the curve actually tells us the probability. So my mean is in the middle, and what defines how stretched out the graph is from one side to the other is the standard deviation. Now, if I take that standard deviation and add it onto the mean and take it off from the mean, that gives me the values, or the likelihood of achieving a value that is within one standard deviation of the mean. I can write this in symbols like this. So that's mean minus the standard deviation is less than x is less than the mean plus 1 standard deviation. And that's about 0.68 for all normal distributions. So all normal distributions will have 0.68% or likelihood of occurring within 1 standard deviation of the mean. If we look at 2 standard deviations, you can now see that this is a bigger area, and nearly all of the graph is actually within 2 standard deviations. In fact, it's 0.95. And the last one is 3 standard deviations. This isn't quite the whole curve. There's a little bit missing there and there, but we're up here now to 0.997. So at 3 standard deviations, there's not really anything left. You have pretty much covered your data set within 3 standard deviations of the mean. Now we have to define our normal distribution in terms of the mean, and we write the definition in terms of the variance. We actually always use the standard deviation in terms of doing any calculations, but the definition itself has to be written in terms of the variance. So this random variable capital X, now this squiggle sign means is distributed by, n stands for the normal, and then in brackets the normal distribution has 2 what are called parameters separated by a comma. You would put the mean first and the variance second. It's often quite useful to write it rather than saying it's a variance of 16. It's actually much more useful to write it's a variance of 4 squared to prompt you that the standard deviation is actually the square root. Now, because we can vary the mean or indeed the standard deviation or both in these distributions, we can create an infinite number of different normal distributions. Here are some examples. But there's one that we use to work out all our probabilities and areas under curves, and that's the standard normal distribution, which is always denoted with a z rather than an x. So z is distributed by the normal distribution always with a mean of 0 and a standard deviation of 1. And your calculator and indeed statistical tables are actually all worked out for this standard normal. So that's what we need to use when we're performing any calculations. Now I'm going to show you how to set up your calculator in the next video.